Okay, our next speaker is a very good friend of mine, Alexey Karapetyants, and I knew him from 2021, where he invited Fernando and us to join a conference in Rostov, and we are very happy that he is here with us and in this conference. Okay, so he's gonna, our friend Alexey is gonna deliver a talk entitled Hausdorff-Berezin and Hausdorff-Zhu operators.
Okay, thank you very much, Paco, and it's my great pleasure to be here to participate in such a great conference. And also, I'd love to say that it's a very good, very beautiful tradition to dedicate a conference to your friends. It's very nice. Well, I will base myself on these papers that recently appeared. Maybe they will be short in order not to disappoint people who want to go to coffee break, maybe. Maybe I'll skip some slides. And basically, I will talk about these first two papers, but some ideas from the other papers I will show also. What are the Hausdorff-Berezin or Hausdorff-Zhu operators? Actually, we invented these notions, and well, it's not regular notions. We just trying to understand what are the classes of operators we can study. But as you see, when you study new classes of operators, or when you invent a new class of operators, you think what are classical operators in your class that are good examples for generalizations. And of course, first example is well-known Berezin transform, which makes a great deal in complex analysis and real analysis. It plays the same role in complex analysis as a Poisson transform, with the only difference that you have integration over the disk, also the same definition you have in a unit ball. And of course, you know that Berezin transform plays a great role in mathematical physics and actually in second quantization procedure and in many, many other issues of modern analysis. So what the idea was, the idea appeared actually when I was a Fulbright professor at SUNY at Albany with Karapetyants, and Karapetyants is exactly Karapetyants operators. So the idea was just because I had free time, I didn't teach classes, so I just thought to invent something. We just thought to invent something new, and what we decided to insert a kernel here. You know what happens if you insert just a general kernel, so you'll have integral operator, and you may consider integral operators, and so on, properties, compactness, boundedness, etc., etc. But again, we had a very nice example in our class, so it kind of first motivation for study classes, just we called Berezin, Hausdorff-Berezin. So, but still, okay, this is the case. I didn't mention that this would be Möbius transform. This is the case of the unit disk. It's kind of easy case. And in the case of unit ball, you have these automorphisms, also very well-known automorphisms, and you can define the same way the corresponding Berezin transform and generalize the Berezin transform for the unit ball. So you can define the Berezin transform, and then of course you can insert here a kernel and consider more general operators. So that's our idea. And well, this kind, what I said, this is the case of unit disk. We put here a kernel. So actually, if we consider general measure here. This is just an example. If you have hard measure, then you can put the transformation here in the kernel. So there's kind of symmetric formula. It's very nice. In some cases, it's useful to consider this particular case because you have the symmetry property. You can get more detailed results. Okay. Well, I said that it's good to have, when you consider new classes, it's good to have some examples in your classes operators. And the main example, Berezin transform, but still we have in our class the so-called invariant green potential. It also realized as our Hausdorff-Berezin operator with a specific kernel given by this formula. And still there are more operators and kind of averaging operators in work by Matejevich and his advisor, research advisor, I don't remember the name now, but they considered the operators to prove Farrelly-Rudin theorem for p between 0 and 1. So this is also a very useful operator, and this operator is also from our class if you consider such a kernel. So having this, let me come back to the first slide. Here's our idea was to take Berezin transform and put here a kernel and consider a general operator, and we did this. And also, when we did this, I came to Zhu, I came to Karapetyants and said, okay, what if we switch the variables? If you put W here and then here, some kind of symmetric switch, and probably nothing happens, but the operator changed drastically. He told me that it's not of interest because he showed me his paper, 1991, where he studied this operator, and this is very small operator, it's one-dimensional operator, so it just takes holomorphic functions and cuts everything except the constant times z to the power 1. So it cuts holomorphic functions. Well, later, my friend Professor Mirotin from Belarus came with a new paper on generalization of this operator. I'm sorry, it was not by intention. And I realized that, yes, this operator is still worth to consider, because when you put here a kernel also change operator very much. Well, I will show you that if the kernel will be holomorphic, then this will be still small operator, it will be one-dimensional. But if the kernel will be different, the situation will change drastically. Okay, so from that time, together with Mirotin, with some other co-authors, we consider these operators as a pair of operators, because now we understand that these operators, although different from each other, still they are of a great interest for developing the theory. Okay, so in my talk, actually, I will not only generalize the Berezin transform, but the opposite operator. So the idea to put here a kernel, like here you see, to put here a kernel and see what happens, and consider the class of these operators. Well, actually, operator of the second type, let me call it second type, is easier to consider. You can apply some criteria, you can even get some nice necessary, sufficient conditions, etc., etc. So let me not take your time on this. As I said, here is a case where your kernel is not only allomorphic, but plus multiplier, plus radial multiplier. Then it acts on
Entonces se convirtió.
monomials like this. So it's almost radial, it's almost diagonal. So it's, as I said, when you have just a holomorphic function, it's one-dimensional. When you put something different from holomorphic function, in the operator change. In this case, for instance, you can calculate the spectrum, etc., etc. So having this, you can go further with some corollaries. You can prove some compactness, etc., etc. So let me show, for instance, theorem about nuclearity in Berman space. Berman space is the intersection of Lebesgue space with space of holomorphic functions, and very well-known Hardy space. So the operator is nuclear in these both spaces, provided these conditions satisfied. So let me not read this theorem. We have also estimation for the nuclear norm for traces, etc. And well, for the case, this was the case of a general kernel, which has a holomorphic part and which has a radial part, non-holomorphic. But let us come back to holomorphic kernels. If you have only holomorphic kernel, a general holomorphic kernel with no restriction, okay, then still this operator is two-dimensional. And you can calculate the action of this operator on holomorphic function as in this formula. Here the additional function is calculated by this series. Okay, so you can estimate the norm of this operator. So the situation changed very much from the case of non-holomorphic kernel to the case of just a general holomorphic kernel. It it's still two-dimensional, as Karapetyants told me in the case when he had kernel phi equals to 1. Okay? Okay, you can have some further results, calculate spectra, etc., but it's easy because you know it's almost spectral representation. Yes, for the operator and Bergman spaces. I will keep this slide also. Again, let's come back to the radial case, because radial case is also of interest. If you have a radial kernel, then your operator is diagonal. You can have some corollaries from the theory. You can prove boundedness in the general space of holomorphic functions with the only condition that this space of holomorphic function, in this space you must have denseness of monomials. That's the only condition that we need to prove these statements, all these statements. Okay, and also we can go further to use a recent book by Serbian authors, Miller, Sarsinovich, and so on, criteria for, or sometimes necessary and sufficient condition for boundedness, because we know the behavior of spectra for this operator, so we can apply the criteria, so sufficient conditions to get boundedness, necessary and sufficient conditions for our operators. But you see, in this theorem, we say our statement is like this. Let spectrum looks like this. Let spectrum behaves like this. Then we have the following boundedness results. But later we decide to put conditions on the initial kernel. It's very natural. Okay, so you don't guess. Just say what are the conditions that we need to have the proper behavior of the spectrum. And to this end, with Professor Grudsky and Mirotin, also we developed a paper based on some kind of asymptotics, so you can actually provide this general asymptotic for the spectral numbers of the operator. And from this we can have many corollaries, and I will not read all the results. For instance, if you consider average of the initial kernel, then you under these properties you will be sure that your spectrum looks like this. The behavior of your spectrum looks like this. Okay, and then you go with abundance conditions and compactness conditions. Okay, again, you know, we can represent our spectra via Jacobi polynomials, and then we can apply what we know from the classical books on Jacobi polynomials, but the results will be weaker. So what we did from scratch, what we did from the beginning was better, because we directly applied the method of stationary phase to the integral representation of spectrum. So this result is kind of weaker. Okay. Well, again, we can formulate properties for the now for initial kernel to have proper behavior of the spectrum, and then actually to have boundedness conditions. Here we have a theorem with some statements you can read. Let me not read this slide. We have boundedness from different between different Bergman spaces here and here also. Well, sorry. Actually, as I said, it worth to consider a general measure. So let me be a general random measure on the ball. We need this property that we call this property tame space. It's written here. We didn't find this property in the literature, so we invented this name, but maybe people know already this property. Well, under this condition, we need to to prove this classes of spaces satisfy to these properties, these classical spaces. But we need this for our technical purposes. And under this property, we can easily prove the boundedness for the general operator with this, I guess, nice condition. Here, the constant depends only on the f. Okay, and here the theorem is for a general space, Möbius invariant space, okay, with the tame property. And actually, we can specify conditions for classical spaces, particular cases as examples, block space, Venetian analytic bounded oscillation space, and Bezoff spaces, Bezoff space of holomorphic functions. So every time constant depends on space, and you have these conditions for boundedness. Going further, considering boundedness in LP, in weighted LP, we invented this definition of admissible weight. We call weight and the unit ball admissible if this holds. This inequality, there is this measurable function, psi z, that inequality holds. And strong property if you have the symmetrical inequality from below, okay, this one. If you have this one, then we call this as strong property. Classical examples of weights, like this weight and every power of this construction is admissible weight, and we can calculate easily the bound for this weight, the function c that appears in the definition. And having this result, we can formulate the boundedness condition in a general weighted space with a general Radon measure. So if this constant is less than infinity, is finite, then we have boundedness in a general weighted space, of course with admissible weight. And to have necessary condition, we need the we have this also slightly different condition. You see here is sigma between 0 and 1, so it can be as close to 0 as you imagine, but we cannot take 0, unfortunately. Okay, so that's why I'm saying that this almost they almost coincide, but they don't coincide, of course. We can specify results for particular weights, for weights of the type 1 minus z squared to the power alpha, which is very important in complex analysis. And of course, you have better conditions for boundedness like this. We don't anymore have a constant. We have just explicit condition for boundedness, sufficient condition for boundedness, and necessary condition for boundedness. And well, also conditions we formulate conditions in some classical spaces. You can see here a very nice condition for Hardy space. Actually, we can apply these operators. Why we consider these operators? Because the initial idea was to transfer what we know for operators with homogeneous kernels to complex analysis. There is a big theory of operators with homogeneous kernels, real analysis, and integral equations with these operators, etc. So we thought that these operators are kind of replacement in complex analysis of this kind of homogeneous operators. It's not actually, but the technique of operators with homogeneous kernels applied to this case very successfully. So we can use this technique and prove some boundedness results, but I will not have slides on this idea. I proceed with last slide of Hausdorff-Zhu operators. Here you have approximation. Actually, it's easy to construct approximation within the LP spaces. Here is just example for nice measure, just not to formulate a big theorem. So this construction that we consider give you a very nice approximation, having in mind that it does not damage holomorphic function. That is a good idea to have in mind that we can approximate a holomorphic function by these nice constructions. Okay, that's the idea. And well, let me repeat some ideas for Hausdorff-Berezin operators, kind of counterpart of Hausdorff-Zhu operators. I will not repeat all the theorems, just some examples. Here, for instance, here I have slides for technique for operators with homogeneous kernels. I'm sorry. So, for instance, if these constants are finite, then you have boundedness in these Lebesgue spaces with higher measure, provided these constants are finite. This constant written here. Okay, so this theorem obtained by the exactly using technique of operators with homogeneous kernels, reduce it to the case of complex analysis. We can formulate some compactness results, but let me skip because I need to say a lot of waste a lot of time for definitions. But you can see the nice conditions for compactness. Okay, so the following theorem holds true for this Hausdorff-Berezin operator. And let me just, I guess I already go further than and finish my talk with this nice example. This has nothing to do with my talk actually, because it's just one-dimensional case. But after we started the study of Hausdorff-Berezin, Hausdorff-Zhu operators, doing things like this, we found a paper on operators of this type. This operator just one-dimensional on the -1 interval, real operator, of course, real functions. So this operator appears in many problems of integral equations and Bezazzi, Lavrentiev equations, actually Prandtl equations, and so on. So we found it very interesting because formally it's a restriction of our operator to the real line. We cannot say this because it's not true. It has no mathematical background, but formally it looks like this. You just restrict from the unit disk on the interval -1, 1, and actually what we figured out that we can apply the same technique to these operators. Now we are in process of the study of these operators, because these real operators, real line operators, also important. And here, for instance, Fourier transform, if you have higher measure, not general random measures, then we can do Fourier transform, Fourier calculus, because it just can be reduced by the real line. Of course, you cannot do this when you have here random measure, what we do with my student now, but this just to show you that these operators appear, for instance, in these general integral equations. And these general integral equations contains these well-known Prandtl, Tricomi, Lavrentiev, Bezazzi integral equations. And we hope we can generalize this technique for generalization of these classical integral equations. Well, thank you very much.
Okay, thank you very much for the extremely interesting and very nice talk. Are there any questions? Or Professor Semyon, please. Oh, yeah. Yes.
I'm talking about invertibility properties. Because you show this approximation result is quite regularization, quite interesting.
This is the next issue that we want to study, because actually we just started to work with this one-dimensional operator maybe just 6 months ago, maybe. But it's a very good question, because when you study integral equations, of course, you want to have
for us it's
a closed invertibility property, of course.
It's quite important for transform theory.
Yes, but also the approximation gives you the idea how to construct the inverse operator.
I don't remember if Mirotin studied these problems.
Excuse me?
Mirotin, our colleague, Professor Mirotin, studied these invertibility properties. I'm not sure.
No, within the place, no.
Because this Berezin generalization could be interesting to invert.
Yes, it's a good idea. That just matter of time, you know.
Okay.
Thank you.
Thank you. My question is this. I would like to know if there is some studies about the dynamic of this kind of operator, Hausdorff-Zhu operator and Hausdorff-Berezin operator. Precisely, if we can iterate this operator and obtain some subsets of operator to compare with the whole space.
To be honest, I don't hear you well and don't understand what your question.
I ask about the product. If we iterate the whole
Product. Okay,
yes.
okay, good. Yes, actually, I skipped the slide, but if you take har measure, then you can multiply operators. You may give conditions under which your product of two operator will be again Hausdorff-Berezin operator. So you can consider algebraic properties, stuff like this. Yes, you can do this. Yes.
And up to now, we don't know the kernel.
I just have one paper in algebra, so I'm not good in algebras. But you know, since your question is very good, because let me find this slide. I skipped this slide, and this is a very good question, also open question. Let me see. Just 1 second. No, maybe it was at the end. Here. See? For instance, this condition, well, this you can consider operators with two variable terms. Because when I insert I use just one variable. But of course you can insert two variables, but under this condition, this is only if and only if condition for the two variable kernel to be the same operator. But more stronger condition gives you radial case in the unit disk. This condition gives you radial case. So you not only have Hausdorff-Berezin operator, but you have Hausdorff-Berezin operator with radial kernel. And in this case, for sure, you can multiply operators. You'll have the same type of operator with another radial kernel, so you can consider algebraic properties, everything like this. So you can do this. But your question is very good because I don't know answer in the case of the unit ball. Here, the problem is open. Whether the same condition will give you the radiality of the kernel. Why I don't know, because in the case of the disk, you just can take Möbius transform, you can calculate one variable from another, etc. But in the case of unit ball, you have such a lot of calculations, so I have no idea how to calculate, you see? What I mean is, W equals to Z. How to find W? It's easy. You apply the same transform. You have W equals to Z of Z. But how to find Z, I don't know in the case of uniball. If I know that I can do the same thing. But this equation is open equation. What we can do it. But again, since I'm not doing algebra, so maybe I just get this.
Excuse me, just about convolution product, I think it's also probably possible to construct some convolutions, a convolution product formula for your kernels.
Yes.
Maybe it's very nice for then construct convolution theory.
Yeah, of course. In the case, the one-dimensional operator in the case of har measure is nothing but the regular convolution of the real line. You just go to the real line.
Exactly. Yeah.
Yes. In the case of general measure, not, but you still can calculate. You still can invent some theory of this same type.
Thanks.
Thank you.
Thank you. Any other question or remark? Okay, then Okay, so then let us thank the speaker again.